Okay, so this was our take-home problem. Take-home problem was a little bit hard, and that's okay. I want the take-home problems to be a little bit on the harder side, so you get challenged. So let's go over this problem. Like I said, it's a harder problem that I probably would put on exam. So here's a voltaic cell. I ask you to calculate the E cell value of this voltaic cell. So if I look at it, first of all, you have to say, okay, here is the line notation for the voltaic cell. The left-hand side, that is the oxidation, right? That is my anode. And the right side is always the reduction, and that is my cathode. So let's go to reduction part first. The reduction part is a little bit easier. What is being reduced? Silver. Again, nitrate is just like a spectator, doesn't really do anything. So the silver is what's being reduced, because this reduction is probably silver plus 1, getting an electron and becoming silver. So silver plus 1 going to silver. That is going to be my reduction. Now, what's going on here? Here is my oxidation. Now, you can also, I emailed you guys 2 long version of SRP table. You have this in your email, and this one is more complete. It has all the fancy stuff on it too. So here, the silver, this is the reduction of silver, and now look at that. There is also an AgCl going to Ag plus Cl minus, and that part is our oxidation. So this part is our oxidation. So I would have to flip this one, right? So here I have Ag plus Cl minus goes to AgCl, and I lose 1 electron. So here, this part is my oxidation, this part is my reduction. And also, you have to really pay attention to what's going on a little bit. If you look over here, technically the oxidation state of Cl doesn't change. Cl minus. Here, AgCl, Cl is also minus, right? But the silver is what's really changing. So far so good. Okay, so we have the 2 reaction going on, and the other way. So look at the table again, and you know that the reduction number potential for silver is 0.8 over here, 0.80 volt, and then this one for the oxidation we have it down here, but again we have to flip the sign. So this one would be minus 0.22. Let me see that 22. Yeah, 22 volt. Again, this is oxidation, so I have to flip the sign. So if I add these 2 together, what I end up getting is, so I have to add up these 2 together. If I add up together, what I end 0.8 minus 0.22, I get 0.58 volt, and is positive. So this reaction will happen. This reaction will be spontaneous. As the way we have it. So far so good. Okay, nice job. And again, this was a little tricky because there's a lot of spectator on here, right? Sodium is a spectator, nitrate is a spectator. The oxidation state of Cl doesn't really change, so it's really the silver that is doing more of the oxidation. They're exchanging electrons. All right, ready for next problem? Let's do another problem. Our next problem, I want you to do again to calculate the voltaic cell, right? To calculate the E cell potential of this voltaic cell. Now again, the same thing as before. Here's my line notation. Don't forget, left side is always oxidation, right side is always reduction. We go from anode to cathode, okay? Now, so what's going on here? On this side, this is my oxidation. What's being oxidized? Cobalt. Cobalt is going to be oxidized. I have cobalt. My cobalt is going to go to cobalt plus 2 and lose 2 electrons again, because this is cobalt plus 2, this is just cobalt 0. Now I'm going to look over here. What's going on here? What's been reduced here? Gold, right? What do I have here? I have gold 3 over here. I have gold 3 that would need 3 electrons to go into gold 0. How did I write this down? Again, look at this. You have to kind of remember Chem 1A a little bit. This is cobalt by itself, cobalt metal, oxidation number of 0. Here I have cobalt chloride, right? COCl2. Where did this 2 come from? This 2 come from cobalt. So here, the oxidation, which is loss of electron, you become more positive. I go cobalt 0 to cobalt plus 2. I have to lose 2 electrons. Now, if I come over here, I have gold 3 chloride. Why is it gold 3? The 3, where does 3 come from? And Cl is -1. It comes from the gold. And this is gold 0. So this is my reduction. So I have to go from positive to a more negative value. So gold plus 3 is going to get reduced. So far so good. Now, what you have to do, you have to look at the cell potential on the table. You have the table. You have the SRB table. If you look at the SRP table, for cobalt, the oxidation of cobalt is what? Is negative 0.28, but you have to flip the sign, so it will be plus 0.28. And the reduction of gold is plus 1.50. If I add them together, 1.78. Yes, this reaction will go spontaneously. This reaction will go spontaneously. So far, so good. Now, before I move on, I just want to make sure everyone knows where I got these numbers from. So this is oxidation, which means it has to be flipped. And this is my reduction. I can just take the number from the table. Right here is the reduction of cobalt, negative 0.28. I have to flip it because cobalt was my oxidation. And gold was my reduction. And the gold is right here. Gold plus 3 getting reduced to gold 0. All the numbers are right here. Cool. All right, so far, we can use the SRP, figure out the cell potential of any cell voltaic cell that I give you. Here's what I want you to pay attention to. What I want you to pay attention to is that so far, everything that we have done, it has been under standard condition, okay? So far, everything has been under standard condition. And what is standard condition again? Standard condition is when you have 25 degrees Celsius, 1 atm, and 1 molar. That's really key. So far, everything has been under standard condition. Well, what if it's not under standard condition? What if it's not under standard condition? Then what do we have to do? If it's not under standard condition, then what we have to use? We have to use the Nernst equation. So if it's not under standard condition, what we have to use? We have to use the Nernst equation. What's the Nernst equation? It's going to be E equal the cell potential minus RT over NF ln of Q. Okay? So let's go over this. Here's my cell potential when I'm not at a standard condition. This one, the E naught cell, that's from the table, what we had before, minus R. What is R? R is going to be the constant, 8.314 joules over mole Kelvin. We had that before. What do you think temperature is? Temperature is, of course, is going to be in Kelvin. N is going to be number of electrons transferred, the moles of electrons that are being transferred, because remember what redox is transfer of electron. Okay, now the F is a constant. The F is a constant called Faraday constant. Faraday constant. This constant is 9648.5.31 coulomb per mole of electron. To be exact, that would be the constant. So far, so good. Okay. Now, ln of Q. Now, what is Q again? Do you guys remember that we talked about Q before? Remember the Q. Q means what? that's the equilibrium constant, not constant, it's the equilibrium product over reactant, and where the concentrations are still changing. They have not reached equilibrium. When a reaction is going on, we can figure out Q to see if we are at equilibrium or not at equilibrium, right? So the concentration matters. The concentration are going to change. So the Q is going to change. So the energy, the E cell will change. I'm going to repeat it again. So concentration matters, right? Because concentration, if the concentration changes, that means Q is going to change. And if Q changes, your E cell is going to change. So again, this is the same as before, product over reactant, that we had the same Q that we had before. So far so good? Okay. Now, if we are at equilibrium, now, if we are at equilibrium, what is it gonna happen? If you're at equilibrium, what do you think is gonna happen? So remember, we had the Nernst equation, and the Nernst equation was E cell equals the E cell at a standard that you knew minus RT over NF ln of Q, and Q matters because concentration is changing. Now, if you're at equilibrium, we've talked about this before. If you're at equilibrium, what does that mean? There are a couple things that matter. If you're at equilibrium, the Q is K. Also, if you're at equilibrium, the E cell is 0. You reached equilibrium, right? The E cell is 0 because you've reached equilibrium. So if I rearrange this, what I end up getting is that E cell naught would equal RT NF ln of K if I am at equilibrium. Okay? So I want you to keep following me, where everything will make sense. There's a lot of math going on, but you guys got this down. So far so good? Alright, now the next thing to consider, I'm going to write down the Nernst equation one more time. So I had E cell potential minus RT NF ln of Q. Okay? If we are at room temperature, now, if we are at room temperature, which is 25 degrees Celsius and 273.15 Kelvin, right? Because most of the reactions are done at room temperature. So if we are at room temperature, that means the R doesn't change, that's a constant, 8.314 joules over mole Kelvin, okay? Now, my temperature is going to be 298.15 Kelvin, okay? Now, over, we said also the F was Faraday constant. They usually rounded to 96,500, okay, Coulomb per mole. Now, what I'm trying to get to, right, here is a Nernst equation, but if I'm at room temperature, this is constant, and this is constant. I have those three values. If I divide those together, what I end up getting is 0.0257. Okay, and what will be the unit for that? The unit for that ends up being joules over Coulomb, which is volt. Joules over Coulomb, which is voltage. So, what did I learn? Here is what I learned. So here's what I learned. As long as I am at 25 degrees Celsius, here's the form of Nernst equation that I can use that is a little bit easier to remember. And that's cell potential, that my E is equal E cell potential minus 0.0257 over N times ln of Q. Did you guys follow that? Again, all I did, here's this crazy equation, except instead of remembering what's the constant for R, what's the constant for F, as long as I'm at 25 degrees, I can plug in those numbers, I can get this, and I can simplify this equation. Okay, do not circle this equation just yet. We can also write this as base 10 instead of natural log. Okay, we can also write this as base 10 instead of natural log. So this is where you have to remember your fancy algebra a little bit. So 0.0257 times ln of 10 ends up being 0.0592. And what I'm doing, instead of having a natural log, I can write this as base 10. Okay, so if I do that, what ends up happening, E is going to be my E cell potential minus 0.0592 over N log of Q. I didn't log ln, I wanted to convert it to log, and I just did that. Now this is the equation that I want you to circle. So we can calculate the cell potential on the non-standard condition. So I'm going to write this down. So here's to calculate the cell potential under non-standard condition. Okay, let's take a step back. I know this was crazy. So this equation, this question that we did, these are all standard condition, right? They're standard condition because of 1 atm, room temperature, the concentration is 1. Standard condition is very easy. You just get the numbers from here, you add up the oxidation and reduction together, you get a number, you'll know if the reaction will be spontaneous or not spontaneous. But what if we are not at a standard condition? If you're not a standard condition, this crazy stuff that we did is to come up with this equation, the form of Nernst equation, and you calculate the cell potential under a non-standard condition using this equation. Are we good so far? Using this equation, you will do that. Okay, let's do a practice problem. So here's the problem. We can do this, just have the SRP in front of you. So again, this is my line notation, right? Here's my salt bridge, which means on this side, this is my oxidation, my anode, right? And this one is my reduction, my cathode. Okay, now this part is easy. Do the easy part first. What's going on here? What's been oxidized? The zinc is being oxidized. Here, zinc is what? Zinc is 0. It's going to go into zinc plus 2 and lose 2 electrons. How do you know that's the case? Because ZnCl2. So that means the 2 comes from the zinc. So zinc goes from 0 to plus 2. So far, so good. Okay. Now, what is going on over here? I have KMnO4. Okay. And then I have MnCl2. Now, here's the way to look at it. You can look at SRP. Actually, the SRP will give it away. But I want you to understand that even if you didn't have a fancy SRP. When you look over here, you have KMnO4 and you have MnCl2. Now, the K doesn't really do anything. That's just a spectator. The same way as here. The Cl wasn't really doing anything. When you add these to water, it would just break up, right? So if you add it to water, this would just break up. If you add this to water, this just breaks up into Zn plus 2. So the same thing over here. So what I have really, it would break up. I have MnO4 minus 1. This is over here. If I add this to water, it would just break up. And I would get Mn plus 2 and 2Cl minus. This Cl really doesn't do anything. It's my spectator. So what I have here, I have Mn plus 2. So hopefully you follow that. Just think about it. So when I'm adding these things to water, Okay, basically I'm adding to water. This would break up into ions. The Cl doesn't really do anything, and I have Zn plus 2, so my zinc is going to be oxidized. Here, this would break up into water. The K doesn't really matter anything. MnCl2 would break up into water. Cl doesn't matter much. MnO4 minus goes to Mn plus 2. This is the what that matters. Okay, now does the oxidation number of Mn changes? Because that's really key. Well, if you remember, we learned if the oxidation number to figure out the oxidation number, we can do this. MnO4, the entire thing is equal minus 1. We know oxygen is always minus 2 times 4 would be minus 8. So the oxidation number of Mn in MnO4 would be plus 7. Okay, so the Mn is plus 7 here. The Mn is plus 2 here. So the oxidation number of Mn changes and it got reduced, right? And it got reduced. Okay, so here is my oxidation and here is my reduction. So far so good. Now, so I have my zinc goes to zinc plus 2, and this is easy to do because I know 2 electrons had to be lost, and I have MnO4 minus goes to Mn plus 2. Remember, we learned how to balance redox reaction. We can completely do that, especially for this one. 1 Mn, I have 4 oxygen. I don't have any oxygen on this side, so I have to add 4 H2O here. Then what I have 8 H over here, so I would have to add 8 H plus to this side. Okay, now we have to balance the charges. What's the charge on this side? I have 1 plus 2 and this is 0. 1 plus 2 and this is 0. Okay, so what I have a charge of plus 2 on this side. How about here? 8 pluses and 1 minus. 8 pluses and 1 minus. So what do I have? So I have a charge of plus 2 here, and over here I have a charge of plus 7. Again, 8 pluses. Oh, I did not just do that. 8 pluses and 1 minus. It would be 7. Now, I have to balance the charges out by adding electrons to the more positive side, which is this side. How many do I need to add? I need to add 5 electrons. Because if I add 5 electrons, the minus 7 minus 5 would be 2. It matches up this part. So far, so good. Okay. So now I have to combine everything together. But before I do that, remember what we talked about. This one lost 2 electrons. This one gained 5 electrons. That cannot be happening. If I lose $10, you gain $10. If I lose $20, you gain $20. These two have to be exactly the same. That was our lecture last time. How do I make it the same? Multiply this one by 5. Multiply this part by 2 to make him the same. Okay. Now I'm going to combine these together. So I would get 5. Don't forget to multiply everything out. Again, we've gone over balancing redox. Go back over it if you still have problem with it. 10 electrons plus 16H plus. I'm going to add all the reactant together and all the products together. Don't forget that you have to multiply everything out. Plus 2 Mn plus 2 plus 8 H2O. Is there anything that I can cancel out? Yeah, definitely the charges. If you can't cancel out the charges, you're in big trouble. Okay. So far so good, yeah. Now, is not standard condition. Is not a standard condition. I know it's not because the molarities are not 1. It's not a standard condition. I know what's my oxidation. I know what's my reduction. I added a 2-half reaction. I balanced this redox. Now, because it's not a standard condition, I know that I have to use a Nernst equation, right? I use a Nernst equation when it's not a standard condition. So, my Nernst equation was E is equal my standard E cell minus 0.0592 volt over N log of Q. That's the simplified version that we did. We put in all the constant that we know for sure and we can plug it in. All right, now let's do this. Okay, to do this, the first thing that we need the E cell potential at a standard condition, right? How are we going to do this? Let's go back to this one over here. You have to look at the table. You have to look at the SRP. If you look at the SRP, what do you get? If you look at the SRP for oxidation, you get negative 0.76, but you would have to flip it. So it would be plus 0.76. And you can even find MnO4 going to Mn plus 2, and that one is already reduction. The number is 1.51. Okay, so if I add up these two together, I get 2.27 volt. Again, how did I get these numbers? The SRP table, right? Look at the SRP table to get these numbers. Here it is. Here is my zinc. I just saw it. Here's my zinc. Zinc was my oxidation, so I had to flip this number, right? And then here is my Mn. It's actually, I even give you the balance equation here, but I wanted you to learn how to do it on your own. So you can look at the SRP and you get these numbers, okay? So that is my standard condition. That's what I would get. So that would be 2.27 volt minus 0.0592. N. What is my N? How many electrons were transferred? This is easy, right? 10 were transferred. This is why I wanted you to do the long way. Log. Now, what is going to be Q? Q is going to be the product over reactant for the final balance equation. For the final balance equation. This is why when it's not a standard condition, you got to do this. You got to do this. So it's product over reactant. I would have the Mn plus 2 to the power of 2, zinc plus 2 to the power of 5, and then remember, water doesn't really count, right? When you do equilibrium, I'm just going to write it and then I'm going to cross it out just so you don't forget that liquid and solid don't count. Then I'm going to come down here. I'm going to do MnO4 minus to the power of 2, H plus to the power of 16, and zinc to the power of 5. Again, how did I get those coefficients? Don't forget all of these coefficients. You don't forget all of these coefficients over here, right? These are all the coefficients that I got, right? Don't forget these coefficients. Okay. Now, I cross that water because it's liquid. I can also cross that zinc because solid and liquids are not part of the equilibrium. Solid and liquids are not part of the equilibrium. So I can cross that water and I can cross out zinc. So, let's do this. I know this is crazy. Don't worry, we're going to do a lot of practice problem. Minus 0.0592 over 10 log. Okay, now look at the main reaction, the main question that I've given you. I gave you all the concentration, didn't I? I gave you all the concentration. Okay, so the Mn, what was the concentration of Mn? It would be 0.25 to the power of 2, and then zinc was 0.5 to the power of 5. I'm going to come down here. MnO4 was 0.10 to the power of 2, and then H plus was 0.01 to the power of 16. I add everything together, I do all the math, I get 2.09 volt. This is a spontaneous reaction. I know this was crazy. I'm about to give you another practice problem to do. But before you freak out, don't freak out. Remember, before our job was really easy. I would give you a Voltaic cell to do. You go, okay, oxidation, reduction. These are standard condition, 1 molar, 25 degrees at ATM. I would just look at this. The oxidation, flip the sign. The reduction, take the sign, add them together, and you get this value. Now, what happens if they're not under standard condition? They're not 1 molar, and then what I would have to do, I would have to use a Nernst equation. Okay, now this is a Nernst equation that is at 25 degrees, and most of the reaction we are doing at 25 degrees. But if you do a non-standard condition, you don't have 1 molar concentration. This is a Nernst equation you use. Now I gave you this practice problem. Again, the thing about this practice problem, the concentration were not 1 molar, so I had to use a Nernst equation. I knew oxidation, I knew reduction. Then what I had to do oxidation, do reduction. You have to balance the equation. That really matters now, because I need to figure out how many electrons are being transferred. Find a balanced equation, then you are going to plug it in. Okay, very nice job. Now what I'm going to do, I'm going to give you a practice problem to do. Okay, I'm going to give you a practice problem to do. Here is your practice problem to get home, to take home. I want you to calculate the E cell value. As you can see, this is not under standard condition. All right, nice job. We went over so much. We're almost there. There's only 1 equation to go over, and we're just going to keep doing practice problem next time. So do this. Before you watch my next video, please give this one a shot, and then I will see you guys next time.